Thank you very much for your patience during our 2 days events of international workshop on wind boundary interactions, exploration and development. We had lots of fruitful discussions, and I'm sure that you agree with me that we have learned a lot during these 2 days of discussion. And nicely done by the previous speakers. They touched upon ancillary services using wind farms, wind turbine generators from different perspectives. I will touch upon the fast frequency response, how it is done, and what we can do to improve it. So let's first go through the UK energy system. What's our perspective for net zero, and then what is fast frequency response, and see some interesting results. Frank from Siemens Gamesa today showed some legacy wind turbines. I'd like to acknowledge that we had wind energy from 3,000 years. So that's a legacy that remained and passed on to us. And the first rooftop windmill was built in Iran near the border of Afghanistan and Pakistan, that they used just clay and wood to somehow collect the wind and just rotate and generate mechanical power. Very simple strategy, but reliable and still in use after 1,000 years, probably more. So, today's modern wind turbines are facing lots of challenges. That this is our duty to sort them out. So, in terms of net zero in the UK, we have strategies for long term by 2050, but up to 2030, we are expecting to have 50 gigawatts of offshore wind power capacity by the next 6 years. Currently, we have 14 gigawatt offshore and 14 gigawatt, almost 14 gigawatt onshore wind turbines. So it's 28 gigawatts, and we found that half of this was by Siemens Gamesa. So to connect these 50 gigawatt fleets, by 2030, we need to invest 54 billion of wiring, which is huge investment. Currently, we use coal power stations just a few hours a day when it's needed. Normally, it's 0%. So this screenshot is from, I think, day before yesterday I took. And sometimes when you check it's 0, sometimes 1 to 3%. And we are expecting to have 70 gigawatt of solar by 2035. We need 10 gigawatt of low carbon hydrogen by the next 6 years. 5 gigawatt of which will be green electrolysis. Previously, the government had different numbers, but in April this year, they raised their ambition. So that's why I just left those previous marks to see that we are transiting to different norms in the UK. Next year, we could see, for example, different numbers. So where are the wind turbines and wind farms located? So we see the onshore and offshore wind farms mostly in Scotland and also the sea terrain. And the newer consent authorized wind farms are getting further and further away from the coast. So there will be a lot of HVDC connections as well. And as I mentioned, we need 54 billion wiring, but unfortunately, laying high voltage cables is too slow, much slower than building new wind turbines. One of the examples is the Eastern HVDC, which are double HVDC lines in 2 phases. We are spending 3.4 billion, and it only accommodates 4 gigawatts of power. By 2027, 22 gigawatts will be operating, and by 2029, it will be full capacity, 4 gigawatts. By then, we will have 50 gigawatts wind ready to be connected. So it's really slow and lagging behind. And wind turbines are getting bigger, heavier, massier, and to me, it's a new source of energy that I'm going to use for fast frequency response, because the blades themselves are super heavy. For example, the biggest wind turbine which has been manufactured by smart energy in China. One blade itself, just each of them is 54 tons. And this is a massive kinetic energy rotating. So I'm going to use this rotating kinetic energy in the mass of the wind turbine as a new source. I will use it for fast frequency response. And so George today was talking about the faster rate of change of frequency and deeper nadirs. When the inertia of the system goes down, what we see is a system more sensitive to disturbances, and the frequency, rate of change of frequency, which is derivative of frequency, will be much sharper. What it means to a system operator is that they only have less and less time to contain the stability of the system. Compared to a system with a better inertia, they have more time to think about a solution to take the frequency near to 50 Hertz. So that means things happen faster and more volatile in a low inertia system. And we need more reserve, we need smarter and faster frequency response. Let's talk about the frequency control and what inertial control is. First of all, frequency normally deviates around 50 Hertz. George was asking about a deadband, why we have it. We have the deadband in electric power system because for around, for example, 0.035 millihertz to not allow synchronous generators to continuously work and operate for primary frequency control. Because frequency is almost never 50 Hertz for a few seconds. It's always 49 plus, 50 plus or minus. So it's just going around 50 Hertz. It's never 50 Hertz. That's why we have a small deadband around it, so to stop generators being activated for primary frequency control. It's like a filter. But immediately after it goes out of that deadband due to a large load connection or a trip of a generator, what happens is that, for example, in a scenario when we have a higher electric power demand in the system, naturally the synchronous generators will slow down and they release a portion of their kinetic energy into the system. Then the primary frequency response will kick in. So that means the speed of the synchronous generators will drop, but their mechanical input will increase. This is a true characteristic of a synchronous generator. And this one would help to contain the frequency after a nadir happens. And it will settle down near the steady state frequency. But after, maybe in some countries, after 4 seconds, every 4 seconds, the automatic generation control by a system operator will send signal to some power plants to eliminate this steady state error and take back the frequency to its nominal value, for example, 50 Hertz in the UK and Europe. For synchronous generator, we can control the mechanical power. For wind turbines, we cannot control the mechanical power because it's wind. For wind turbine generators, however, we can control the electric power. So we are going to use this advantage. Now the question is that what if we could control the electric power output of the wind turbine generator to help us for the frequency containment, frequency yield improvement, and hence enhancing the security of the system. By the way, we do not have automatic generation control in the UK, which may sound strange. So what happens? We just take the phone and call some of the power plants to increase their power output in a traditional way. So let's quickly see what sort of frequency response and frequency control schemes are available. The fast frequency response, just the idea first started around 2004, appeared in literature. Probably industry was working on it prior to that, but whatever literature revealed was around 2004 that people were discussing about. We need some sort of inertial control or synthetic inertia to inject to the grid and help sustain the frequency. there are different types, but if I want to categorize them into different groups, I would say there are frequency-dependent inertial control, where we sense the frequency deviation and multiply by a proportional gain, and we call it inertial loop. Or the difference between the nominal frequency and the actual frequency would be a Droop loop. So these are frequency-dependent inertial control. However, we have another sort of frequency control scheme, which is predefined or pre-designed control schemes. We call it stepwise inertial control. And there are some pros and cons. Normally, stepwise inertial controls, which are predefined, can improve frequency nadir much faster. But we have to be very careful when we design them because they're prone to make the frequency control worsen, which I will show you shortly. Let's see what is a stepwise inertial control. Well, mechanical power input of the wind turbine generators are a cubic function of the wind speed, as you know, and normally we operate in maximum power point tracking. That means we focus on extracting maximum power from the wind. That is our primary goal when we build the wind turbines. And they normally operate within some boundaries. They cannot be too fast. They cannot run too slow. Otherwise, they will stop rotating. And they normally rotate at their MPPT mode. But when a disturbance happens in a system, we require fast frequency response. How it is done is that we immediately increase the electric power output of a wind turbine generator. And in this way, what happens, the electric power output of a wind turbine generator is higher than the mechanical power. Therefore, mathematically speaking, the rotor speed should drop. And that's what we see here when we are in overproduction mode of a wind turbine generator during the inertial control, the rotor speed will drop. So we don't want to see it go below 0.7 per unit for example, DFIG. And we have to stop this action by switching back, for example, to MPPT mode or go below the mechanical power curve. Then the rotor will have this capability to go back to its previous working point. And let's consider a scenario when wind turbine does not participate in frequency control. We have a deep frequency nadir. Now, if the wind turbine generator operates in inertial control mode, we improve the frequency nadir. However, when we terminate this action, this is another disturbance from power system point of view, which causes a secondary frequency drop. Therefore, remember that the first frequency nadir is due to a disturbance from power system. The second frequency drop is due to a disturbance from the wind farm or wind turbine. We caused it. So when we do different scenarios, for example, when to terminate, earlier, later, we will have different possibilities. Secondary frequency drop could be better or could be worse. In fact, in most cases, could be worse than the cases when they didn't even participate in frequency control. Therefore, we have to be very careful when we design inertial control schemes. And one solution we have come up was, we were thinking of a solution, easy to understand by academia, easy to understand by industry, easy to be implemented, trustworthy and reliable. So one idea was Gaussian distribution, which is a function naturally happening in nature or in socioeconomics, in statistics. So this is a function that it's a data scattering around a mean value and can be measured by a standard deviation. That means if the standard deviation becomes bigger, the data will be scattered away from the mean value. A simple idea, a simple function. So we are going to use this Gaussian function for inertial control or fast frequency response. How to implement and develop the mathematical manipulations behind it is that we have the Gaussian function and we just use it for inertial control by just manipulating the mathematics behind it. For example, the mean value could be the active power, the working active power of a wind turbine, and then instead of, for example, function x there, we have the rotor speed of a wind turbine generator. So then another question would be which trajectory I should choose that would best fit for my inertial control or help the grid. And we came up with the solution that if we use the point that the rotor speed, when we land on a mechanical curve, on an equilibrium point, be between the working point or MPPT mode and the minimum allowable rotor speed, that would be the best equilibrium point. Then a Gaussian function can help us to have maximum frequency response. So with this, we came up with the conclusion that the standard deviation of the Gaussian function can be a control parameter for inertial control. And
in your graph,
oh, sorry.
you have a yellow curve and you have a red curve. What is a yellow curve?
The yellow curve is the mechanical power of a wind turbine, which is a cubic function of wind speed. And it's a nonlinear function with the tip speed ratio.
And the red curve?
This dash red curve is electrical power of a wind turbine generator, which is a cubic function of a rotor speed. K multiplied by R cubed to the power of 3. But we can only operate here. Why? Because electric power output of generator, wind turbine generator, will be equal to the mechanical power. Therefore, in swing equation, we don't have rotor speed deviation. This is the MPPT mode here. So that means the wind turbine is operating at the maximum point of this curve, the mechanical curve. We are going to harvest the maximum power from the wind. The point is here. So we are working at the P0 as MPPT mode.
No, actually, your red curve is all the line of the maximum point for different
From different wind speeds, yeah, from the different wind speeds. Thank you. But this one is for just for example, 11 meters per second. Yeah. At this point, the maximum point is P0, which wind turbine is operating at MPPT mode. When we are here and we want to inject incremental power, we need to go up, not down. Then we create more power, right? So where this power is coming from, if you ask, is coming from the stored kinetic energy in the rotating mass of those hundreds of tons of blades. So I'm just extracting a portion of it. And again, why I chose that medium point, we were taking into consideration different criteria. One, we need the frequency nadir to improve, be near 50 Hz. The second and most important part that some might forget is that we want our settling frequency be above the steady state frequency. In some countries, probably you heard from me day before yesterday, that if you go below a certain frequency, your secondary frequency control will not be activated. So you have to make sure your steady state frequency is above that threshold. In Europe, it's 0.02 Hertz or 200 millihertz. Well, sorry, yeah, 200 millihertz. So also, we particularly are interested in this medium point that it allows for cascade events. That means if, let's say, a frequency event happens, you're helping for inertial control, and immediately after a few seconds, again, a second cascade event occurs. We still have more action to play here. For example, we landed here, we still have kinetic energy, we can inject extra power and come down. So it allows us for more actions. Now, if I choose small standard deviation, that means I inject incremental power and then land quickly. In this way, I have high settling frequency. That means the settling frequency will be very high, but I will have deeper nadir, which is not very good for me. I need to improve nadir as well. If I choose a large standard deviation, that means I inject active power and then I use, for example, this trajectory, I land very far to reach an equilibrium point. I will have a better frequency nadir, but I will have lower settling frequency. That means my steady state frequency error will be high and stay there forever unless the AGC be activated manually. Where is best? We have standard deviation when we have the rotor speed and average speed between your working point and your minimum allowable point. So this way, analytically shows that we have high settling frequency and also high nadir, which is advantageous for both wind farm owner and operator. So we did them. We did some tests using simulations in Deep Silent Power Factory on IEEE 9 bus, and we compared it with some existing methods that they theoretically discussed in the literature. And as you see here in the green, solid green line, frequency nadir is quite acceptable compared to the existing methods, and with good settling frequency. And with different wind speed, also we took into account the change in the wind speed during your inertial control. Also, the rotor speed will converge earlier compared to different methods to an equilibrium point. We tested in bigger power system scale, IEEE 39 bus system with different scenarios, also cascade events. What if, for example, after a few seconds, we have a second frequency event? So it stayed robust, and this is a second cascade event, not a second frequency drop. So it also showed its reliability. We stepped further to see what would be the action if we contribute to inertial control. Does it damage the mechanical shaft, or it would have some stress on the mechanical parts of the wind turbine? And as we see, for example, the methods, the results are quite close to the maximum power point tracking mode. That means it sounds like you're working at MPPT mode, because you're just injecting for a fraction of maybe a few seconds, and that's it. So it doesn't really affect your mechanical stress and fatigues. You don't impose fatigues on your blades. So we did some real-time simulation tests at Warwick, at ICSE, and we did, for example, some two-area systems. If the event happens in area 1 and your wind farms are located in the same area, your contribution of inertial control is really significant. But if the event happens in a different region, far away from your wind farms, your contribution wouldn't be very significant. You still help to improve the frequency nadir, but not that significant. So, which is understandable. If the frequency event happens to be near your wind farms or in that region, we are, for example, lucky. Or another solution would be we have to have coordination where the fault has happened, that event happens. If there are wind farms nearby, if they can contribute more, would be better than some wind farms much further away in Scotland, for example, if the event happens in south of the UK. So just wanted to show some hardware in the loop test as well we did on inertial control of wind turbine generators. So we developed a microgrid system of PV, wind, diesel, battery, and liquid air energy storage as well. So a blend of different energy sources to use hardware in the loop and see the performance of inertial and droop control for frequency containment in this microgrid system. So we use our existing emulators, and we use OpenRT real-time simulator and developed the model in MATLAB Simulink, and just simply explaining that you have the functionality of activating and deactivating each of these elements in real time, or you can control the gains of your inertial and droop controls in real time. You can apply when your frequency event can occur. And just to show you the results, for example, when the frequency event occurs by, for example, disconnecting from the grid, you see that frequency is deviating from 50 Hertz, and your controller is trying to get it back to 50 Hertz in just a few seconds. So these are the real-time simulation we tested in our lab. And the conclusion, so we developed a Gaussian distribution-based inertial control for wind turbine generator. In my opinion, easy to be implemented in practice, and it allows cascade events. If two consecutive events occurs, you have the functionality to play with and inject incremental power. And the results were compared in different IEEE standard networks in Dick Silent, and also with literature. It showed its robustness from mechanical perspective and electrical perspective. All right, so that's all from my side, and thank you very much.